Alright, welcome to this video in which we're going to take a look at the bubble sort algorithm, and we're going to take a particular focus on analysis of the bubble sort algorithm. As motivation, we'll take a second to talk about searching a list. Of course, one of the important reasons why we might want to have a list sorted is it makes searching a little bit easier. So let's consider our possibility here. First of all, if our list is unsorted, if we want to find an element in the list, we are limited to a straightforward brute force check. That means we're going to look at every location. Typically we're going to call this a linear search, and that's because the runtime of this is going to be big O of n, or order n, meaning that on a list of size n we expect to look at all of the elements, well, that would be in the worst case. In the case where maybe the element we're looking for is not in the list, we need to inspect every element in order to rule out the possibility. Alright, so let's say we sort the list now. Are we able to find the element a little bit easier? And of course, the algorithm we use in this case is called binary search, similar to a phone book or dictionary search, where you look in the middle and compare the element to the one that you're looking for, and then you can rule out half of the elements on each check. Of course, the runtime of a binary search is asymptotically better. It is order of log n instead of n, and so that means we're able to find the element quicker if the list is sorted. Of course, that's why we're going to want to keep our list sorted. Here I have stated the problem of sorting a list as a information processing problem. In computer science, we tend to focus on the input and output relationship when stating a problem, and then we rely on an algorithm to map the input to the output. So again, an information processing problem is a relationship between the input and the output, and then an algorithm is used to fill in the in-between there, that is, transform the input into the output. That opens the possibility that for any given problem, that is just the input and output conditions, we could have any number of algorithms that fills in that in-between bit, mapping the input to the output. And of course, part of the goal of algorithm analysis is to compare those algorithms that we might have and use those comparisons to select an appropriate algorithm. So here we have the bubble sort algorithm, one version of the algorithm that I've written in Java. And we're not going to maybe look at all of the details here, but maybe let's remind ourselves of how the bubble sort algorithm works. The bubble sort algorithm works by comparing two neighboring elements, and then if those two elements are out of order, it simply swaps the two elements. And we can see this here in the inner loop. Our inner loop here, we are indeed comparing element j to element I, or j plus 1, and if they're out of order, we swap the two elements. And then this is, we carry this out in a pass, a single pass, where we start at element 0, and here we stop at this particular element. This is stopping early, and maybe I'll comment on that in a second. But we could stop at the size -1. But in this case, we're stopping after we've checked in our pass all of these pairs, the neighboring pairs, if they're out of order. Now, let's think about our first pass. In the first pass, our I is 0, so we stop right before the last element. In that case, we have we've gone through the entire array and compared one element at a time to its neighbor and swapped them if they were out of order. Now, imagine as we're going, we encounter the maximum element in the list, and when we do, we'll notice that as we compare it to its neighbor, it will always be greater than its neighbor by definition, since it's the maximum element. What we can confirm after one pass, then, the maximum element will have floated its way, or bubbled its way, up to the top location of the list. This is why in the next iteration of the list we don't have to go quite as far. We already know that the maximal element is in the correct location, so now we'll find the second maximum element, and so on. Of course, we may have to do this one time for each element, except for possibly the last element. If all of the other n-1 elements are in the right location, then we are guaranteed that the last element is as well. So again, we see that we are stopping one early on our outer loop as well. Okay, the goal of this video then is to actually analyze the number of operations carried out by this bubble sort algorithm. And maybe you already have a good guess for this. Maybe you've already encountered this in your own studies, what the runtime of a bubble sort algorithm is. But if not, I'll state our bound here is going to be big O of n squared, or order of n squared. And so it's going to be the goal of this video to demonstrate that with a little bit of math. Before we do that, I want to talk a little bit about some of the concepts involved in our analysis. And the first thing is we're interested in talking about operations. We're going to be counting operations. And why are we counting operations and not something else? Normally we measure the amount of time something takes in units like seconds. However, seconds aren't a very useful measurement for measuring the runtime of algorithms, and that's largely because as our technology improves, the number of seconds that a particular algorithm might take might go down, and we want to have a comparison between algorithms that is not sensitive to the changing of technology. We want it to be insensitive to those changes. So we decide to count the number of operations carried out by the algorithm instead. So then that raises the question at hand here, which is, what are we counting as an operation? And so here I have a few possibilities. Are adding two numbers together a single operation? We may have some intuition here, and we may already have some experience treating simple arithmetic like addition and multiplication as a constant time or taking a single operation. However, you may know that, or you may start thinking that if our numbers get kind of large, then the amount of time it takes to, say, add together two million-bit numbers is certainly going to take us longer than it takes to add two, say, 32-bit numbers together, which is a more common process that we do. So there may be situations where we want to count these as a single operation, and then there may be situations where we don't want to count these as a single operation. And so this means our analysis needs to be sensitive to the purpose that our analysis is going to serve afterwards. The last one I have here is certainly one that we might think is going to take more than a single operation. This is comparing two strings to see if they're the same. If you've ever had to write a function to do this, you know that we're going to iterate over the characters in the string, and of course to do that we're going to take more than just a constant number of steps. We're going to take a number of steps related to the length of the two strings involved. Alright, I mentioned that what counts as an operation is going to depend on our purpose, the purpose that we want to put our analysis to. And so our purpose is going to determine what I call our resolution of our analysis. We can have a rough grain resolution or a fine grained resolution, or we could have sort of a low resolution or a high resolution. With low resolution analysis, we may try to ignore most of the operations and focus in on a very single kind of operation. Maybe we'll just count, say, additions, or maybe we'll just count outputs to the console, or maybe we'll just count accesses of the network. Very, very specific operations. In these cases, that usually we might do that because it makes things a little bit easier, as opposed to a very fine or high resolution analysis, in which case we are focusing in on all the details. We want to count every single operation. We might even be counting bit operations that are carried out in the machine if we do a very fine level analysis. Now typically, as computer scientists, we occupy somewhere in the middle. We want to count most of the operations. We don't want to leave out any that are important, but we don't need to get all the way down to the nitty-gritty every time and start counting, say, bit operations. All right, so say we're operating in Java then. What kinds of operations in Java might we want to count as a single operation or as an operation that takes constant time, which we're sort of going to use those ideas interchangeably, constant time and maybe a single operation as being the same idea. So what kind of operations? Well, here I've listed a number that we should expect to be constant time. Declarations, declaring a new variable, that's asking for memory. Assignments, that's obviously changing a memory location. Doing some arithmetic, constant amount of arithmetic takes a constant amount of time. Same thing with logic, say logic in an if or a while statement. Branching, again making the choice to go into the if or into the else. And then maybe more importantly is many method calls that we might make from, say, a Java object of any kind, but a Java data structure that we might be using. Many of the method calls are going to be constant time as well, and if you're interested in that, this is a good reason to go visit the Java docs and take a look at the documentation for the method that you're looking at. Usually there will be a comment about what the expected runtime is, and in particular for the linked list and array list that we looked at in a previous video, you can find some of the discussion that we found or that we provided there in the Java docs. With that said, there are also a number of methods that are not constant time, and so you should be sensitive to that as well. So sometimes we can get into a bad habit of thinking that any method we call from some data structure that we've instantiated is going to be a nice fast execution. Well, we're probably going to get out of that bad habit after looking at a couple of data structures in this series of videos. Okay, so I've been using the phrase constant time here, and I want to again review or refresh what I mean by that. Well, specifically by constant time I mean that it's going to take time in big O of 1. Well, again, what exactly does big O of 1 mean? Well, let's recall that big O of 1 is a set of constant functions. And so which constant functions are in there? Well, I've got some examples here. Well, 1 is the representative constant function. It's the one we use sort of as the name of the set. Big O of 1 is the same as big O of 2, but we usually name it big O of 1. So 1 is a constant in this set, 42, 1337, 1701, 1 billion. These are all constants. Now I've sort of put a handful in there to say, okay, these are all constants, but I put 1 billion in there to remind us that even if a constant is quite big, it's still a constant. So if we have some operation, some function that takes 1 billion operations, but it takes 1 billion operations no matter how large the input is, then that's still a constant time operation, and so that's something we might want to be sensitive to. And the reason I want to say that is there's not really a good point for us to draw a line and say, well, below this, below 100 operations, that's constant, and above this, it's not. All constants will do. So even 1 billion times 1 billion is going to be a constant, and so on. We can get a little ridiculous. So typically, we don't actually know the constant involved. It might be 7 or it might be 42 or something like that. And since we usually don't know the constant involved, and also usually we don't care that much about the constant involved, it's not as important to what we're going to use it for, we'll usually just give it a name. And in mathematics, and computer science, the convention is to give constants names, lowercase letters from the beginning of the alphabet, like A, B, or C, also D or E. C, of course, standing out for constant. We use C usually when we have no reason to use anything else. And then maybe also importantly is if you have a constant, you can take that constant and put it through any function, and you're going to get yourself another constant. And this is something that's important because if you have, say, C and D and you go C plus D, well, that's still another constant. And we're going to get in the habit of renaming our constants. So if we get some that are gathered together, A plus B divided by D and so on, we might just rename that, okay, we'll call that C new or something like that, and we'll just give it a new name so that we don't have to carry along these long collections of constants that are being lumped together in using functions. So here I've listed a few functions, and maybe the last one here is worth looking at, this C to the power D times E factorial. Again, this is probably going to make a really, really large number. But as long as they are all constants, what pops out is still a constant. So we need to keep that in mind. Now, how do we change a constant? How do we get something that's not a constant then? Well, the way of doing that is by introducing a variable. And we usually use the variable n or m in computer science, or x and y in mathematics, as variables standing out from the constants. And again, that we use the lowercase letters at the beginning of the alphabet for our constants, and we'll usually use ones near the middle or near the end for our variables. All right, so let's take a look at another example here. Let's say we have looked at the array list functions get and set. We've looked them up in our Java docs and our Oracle documentation, and we've confirmed that yes, these two functions are constant time functions. And the reason they are constant time functions in our array list, going back to an earlier video, is that we have random access. To these indexes, meaning that the cost that it takes us to access any index is independent of what that index is. It's a constant independent of that index. So because of that, we know that these two methods take constant time. And again, following our pattern above, we don't know what those constants are. That's not stated for us in the Oracle documentation. So we might as well just give them names. And so I've decided I'm going to give them the names cget and cset. Okay, and then let's consider the task of swapping two elements. This is a subroutine that we were using in our bubble sort algorithm that I didn't actually show you, but in the swap method, and I'm sure all of us have had the experience of doing a swap before. In a swap, if you don't want to have a bug, you need a little bit of temporary memory as well. We end up doing 3 assignments. We'll copy them one element into the temporary memory, we'll copy the second element over the first, and then we'll copy the first element out of temporary memory back over the second element. So this subroutine is again one I wrote for this example, and it used two gets and 2 sets from my array list, plus a little bit of extra work, which is the temporary memory is used for. And so I went ahead and I said, well, the total cost then is given by this method here, or this function here. 2 gets, 2 sets, plus some extra work. And then following the pattern I mentioned above, I'm just going to lump, those are all constants. We're putting them through some functions. I'm going to lump them all together, and maybe I'll just say, okay, the swap subroutine that I wrote also takes constant time. And I'm just going to call that one cswap or something else if you have a different name you want to call it. And again, that makes it easier so that in our calculations we don't need to carry this conglomeration of other constants together. We'll just carry this one along, saving us some writing. All right, so back to our bubble sort algorithm here, we're going to want to again ask the question, well, how many operations is carried out by this? And keeping in mind that again the number of operations is going to be dependent on how large our list is when we start out here. Now I've stated here, let's say that our list is of size n. So our list.size here, when we call that, it's going to pop out our n. Okay. And again, we might want to look and say, let's do a quick look here. What methods are we using in here? We have some arithmetic showing up here and there. We know there's going to be a check going on in our for loops and so on. So all of that stuff we've already identified as constant time operations, the negation here, constant time. So what we really need to do is look at some of these methods. We've got the get. We have said that's constant time. We've also got the size method here. That's also a constant time method. Okay, so all of these methods are constant time, so that's something we can comfortably move forward with. So for instance, if we want to know what the cost of this loop body is here, how much? Well, it's a constant plus a constant, and then we're doing a comparison here. There's some other operations that might be carried out. Remember, our swap operation is a constant too, but adding those all together is just going to give us one other constant. So in the end, we're going to say, okay, the cost of this loop body is probably a constant, and that's all that matters. What the constant is not going to matter to our asymptotic, our big O analysis at the end, so we do not need to keep track of what that constant is at this point. We'll just start lumping them together. Okay, so there is a question posed here that says, is this still going to be true if we started using a linked list instead of an array list? And this is something I want us to be sensitive of. Remember, the primary distinction between these two lists is our access. With an array list, we have index-based access, but with the linked list, we do not. These get operations actually take order of I to access the element in index I. So because of this, that doesn't mean we can't use a bubble sort on a linked list. It just means we don't want to use this version of the code, because this one makes use of the get calls, something that is not reliable for our linked list. So keep that in mind. Maybe a good exercise would be, if you're a Java programmer, go ahead and try and convert this Java code into one that's going to work for a linked list as well, or instead. And my hint here is, of course, you're going to want to use an iterator instead. Okay, so again, it looks like the most of the work that we need to worry about is being carried out inside our two for loops here. So let's go ahead and try and analyze those in a little more detail. And to do that, we're going to use a summation. Okay, so to find the summation that we're going to need to use, we're going to, well, we have a nested loop, so we're actually going to end up with a nested summation, where we're going to use an inner sum for the inner loop, and then we're going to have an outer sum for the outer loop. So let's take a look at the sum that I've created here, and let's make sure that we've got the values correctly. So to do that, what I want to do is compare the sum I've written here to the structure of the two nested for loops up here. Luckily, when we have for loops like this that have the indexes stated right for us, specifically when they're doing increment as their operation, then we can translate them into summations directly by copying those indices. So I've done this very deliberately. I've said, okay, in my for loop I have I equals 0 to n minus 1, or list.size minus 1. I'm going to rewrite that in my summation almost exactly the same. I equals 0, and then my upper bound is, well, I don't have a list.size down here. That's where that n's coming from. N is going to be my list.size, so n minus 1. Okay, that's my outer loop. And then let's look at the indices again on the inner loop. Again, reading directly from the loop. J equals 0, J equals 0. Now this one we need to be a little bit sensitive. we've got, again, list.size is our n, but it's n minus I minus 1. So n minus I minus 1. All right. Again, what about the rest of the loop? Well, let's look at the inner loop here. We already did a quick argument to say that this loop body is going to be constant time. I should mention there are a few other things going on other than just these 3 lines of operations. We're also going to be doing in each iteration of this loop, we're going to do a check here, which means we'll probably have to call the size function. We'll do a minus and a minus. We'll also do an increment at the end. So in every iteration of this, there's a little bit more extra work going on up here as well. Okay, again, it's all a constant, so we're going to lump that all together, and I've named this constant b for this problem. Okay, outside the loop, in our outer loop, we also have a little bit of extra work going on. We have, it looks like we're going to be setting this flag every time and then maybe checking it at the bottom. Notice this is a special early exit that we build into bubble sort. Let's maybe just check what this early exit does for us. So I've set my inversion to false up above here. Notice I only set it to true if I make this swap. That means I only set it to true if I find 2 elements that are out of order. Notice if I never find 2 elements that are out of order, that means they must all be in order. And so I've got a simple break here telling me to break out of my loop in that condition. Okay, so the reason I was looking at that was, again, to say, well, what extra work or what work is being carried out in this outer loop? One of the things carried out in the outer loop is the inner loop, but we've got that captured already by this summation. So we only need to worry about anything else other than the inner loop. And for that, it looks like we've got a few operations down here. Again, a little overhead up here, maybe an operation here. Still a constant amount of work. And so I've decided to give that a name, and I've decided to give it the name A. So this is the function that we want to use to express the number of operations carried out by our bubble sort algorithm. Now what we want to do is simplify that a little bit using some of the mathematic techniques that we're familiar with. So let's take a look at that. So let's begin by refreshing our memory of a few steps here. There are a couple different ways we can start out here. One is we can start with this interior sum and solve it, noticing that it's independent from the outer one. The outer sum depends on the inner one, but not the other way around. So it is safe to get started on that inner sum right away. Or we can distribute our sum, and that's sort of the instinct that I have here. I want to distribute my sum. All right, so when we distribute this sum across our 2 terms, we end up with getting 2 different sums. The first sum is just the sum over the term A, and then the second one is the sum where we get now a nested sum. This whole sum is the term we sum over on our outer sum. All right, now the next step I'm going to do is I'm going to notice that the A and the B do not depend on the indices that we're summing over. So A does not depend on I, and B does not depend on J nor I. So that means we can bring them out front. We can factor them out of the equation. So that's my next step. All right, so in this step, I have factored the A out front of my first sum, and I factored the B out front of both sums. All right, that makes our sums a little bit easier to solve. Let's look at the first one here. Here we're going from 0 up to n minus 1, and we're just adding that many ones together. Now that one's a little bit tricky to look at. We can probably have the intuition already to see that since we start at 0, we actually get n elements here. But one way that we can figure this out, maybe just as an aside here, is if you want to know the number of elements in a sum, you take the upper bound, you minus off the lower bound, and you add one more. And so we can see here our minus 1 and our plus 1 are going to cancel out, and we get n. So there's actually going to be n terms in this sequence. So we can write this as, an. So this one's going to end up being an. All right, let's continue. In this term, Now, we can't just simplify the whole thing all at once, but we might be able to simplify the inner one using the same technique, which is looking here, we just have ones here. So how many terms in this sequence? Let's be careful again. Let's use our formula. We're going to take the upper bound, n minus I minus 1, minus the lower bound, but plus 1 more, so our plus 1 and our minus 1 cancel. And we get n minus I as our term. So I'm going to be careful now. I'm just going to rewrite this inner sum here as n minus I. So we now get b. All right, so after simplifying that sum, we now have that n minus I term we calculated here, substituting in for that whole sum that we simplified down. All right, let's continue a little bit further. And we're going to notice here, I'm going to just bring the a n down as it is, plus my b. But now I want to distribute my sum over these two terms. So let's do that a little bit further. Okay, so distributing the b, or the b and the sum over our two terms, we're going to have b with the sum from I equals 0 to n minus 1 of n. That's our first term. And for this sum here, I've taken the minus here and I factored it out front. So we end up with minus b with the sum of I equals 0 to n minus 1 of I now. Okay, of I. All right, so we should be able to continue a little further. We're still going to have our a n. Plus now, this term n does not depend on our I either, so as before, I'm going to bring it out front. I'm going to get my bn. We just have a 1 there now. This one we might simplify down to another n. We'll see in a second, but I'll leave it as that for now. I am going to leave this other term just as it is. That one looks a little bit trickier. Some of us might already know what it's equal to. But if not, we'll come back to that and look at that one in more detail. Okay, so yeah, let's do the one last step where we take this sum and replace it with an n. So we now have a n plus a b n squared, a bn times another n, minus this sum that we need to solve, I equals 0 to n minus 1 of I. All right, this sum here looks a little tricky, but it's going to be a little bit easier if we solve it by looking at a slightly different sum. Slightly different, it's 1 to n instead of 0 to n minus 1. And this sum is called an arithmetic series, although I sometimes call it Gauss's sum, because I remember this as a story about the mathematician Gauss, who as a child, I believe he was about 10, was asked by the priest who was teaching him arithmetic to solve the following problem. 1 plus 2 plus 3 plus ... plus all the numbers to 100. Okay, so he was asked to do that. Now, the priest would assign these hard arithmetic problems to their students so that the priest could take some time off, visit the pub across the street, have a couple beers, come back after lunch, and hopefully the students had completed their assignment. He would also at the time bring his slate over, his chalk and slate over, and probably work out the solution himself, probably not knowing it ahead of time. But this day, Gauss was in his class, much to his dismay, and Gauss, well, he didn't already know the answer, but he quickly, before the priest was able to leave for his lunch and his beers, said, oh, okay, I think the answer is 5,050. To which the priest said, you know, how do you know that? I don't know that, because the priest didn't know what the answer was. The priest had to go solve it himself. But let's take a look at how Gauss actually figured this out so quickly. Well, what Gauss did is he noticed a pattern, and he's a bright guy. He noticed if you add the first and the last number together, you get 101. You notice if you do that for all the pairs, you can keep going. you keep getting 101 all the way down until the last two numbers, which are 50 and 51, also add up to 101. So the question then that remained is, how many of these pairs were there then? Well, we had 100 numbers to start out, so there must be 50 pairs after we pair them up. Gauss didn't need to do too much work. He just had to do, okay, 50 times 101, and he was certainly bright enough to do that. And he did that and came up with the solution. So that's pretty clever. Let's see if we can mimic it. Here I'm going to replace 100 with n, and then this will be n minus 1, and so on. And what we'll see here now is if we, I'm going to write it down here. If we take our two numbers together and we add them together, our first one and our last one, first one, last one, we get n plus 1. How many such pairs will there be? Well, there are n elements in this list, so there must be n over 2 such pairs. So this formula that we have here works for any value. Gauss had to do it to 100, but we have to do it to n. So we get this value here. Now let's go back and take a look at our sum a little bit closer. We'll notice that it doesn't start at 1, it starts at 0. But that first value, I equals 0, is just adding 0. So adding 0 onto the beginning of this doesn't change the value. So we technically could just say, okay, we don't need that. We could change that to 1. Okay, the other thing we did though is we have a different upper bound. We're not adding that last element on the n. And I guess there's two ways we could do this. One thing we could do is we could minus n off this, because that's the last term. That would give us the value. Or alternatively and equivalently, what we could do is we could recalculate our formula here. So maybe I'll do that. I like that idea. So now we have n minus 1 as our upper bound instead. And I chose 1 here because the 0 is really irrelevant. So again, using Gauss's idea, what would we do here? Well, taking our first element and our last element and adding them together actually gives us n, not n plus 1 like we had before. And now how many elements are there? Well, there used to be n, so now there's n minus 1. And again, pairing them up means dividing by 2. So we actually see here, and you can verify if you want, that adding n to this sum here gives you this sum here. Okay, so it's sort of, you can go ahead and verify that on your own. But this one's the second one here. This is the one that we actually want. This is the one we need. So let's use that one to complete our analysis. Okay, so after substituting out this sum here with our closed form expression of it, this one here, we can now, all we need to do now is some algebra to simplify a little further. I'll mention that if you didn't already know what that closed form of that sum was, well, now you know it. It's definitely worthwhile to remember that, write it down on somewhere that's easily accessible. If you are going to encounter these types of sums again, you're going to want to know some of these closed form expressions by heart when you encounter them. All right, so we've got here. Let's just continue, I guess, multiplying out a little bit. We got an. Our bn squared comes down the same as before. Looks like we're going to get a minus bn squared, but let's be careful. Bn squared is still over 2. Otherwise, we'd get a full canceling out here. Looks like only half of it's getting canceled out. And then again, being careful here, we have a minus b times a minus 1. That's going to give us a plus. So the next term is going to be a plus b, and it looks like it's an n over 2. Okay, bn over 2. And usually for completion here, it's worthwhile for us to gather our like terms together. So first of all, this one cancels out kind of nicely. I'm going to write it as b over 2 times n squared. Here, isolating the constant coefficient, right? B over 2 is a constant, n squared is the variable. And then let's be careful here. It looks like we have an an and half a bn. So again, if we want to isolate the constant, I might write that as gotta be n. Okay, and again, I've gathered the like terms, I've isolated the constant coefficients, and then I've also listed them in decreasing order of degree, so that it's pretty easy for us to conclude here that we're looking for a big O here, and we can see that this is big O of n squared. All right, so we did our analysis, and we came up with big O of n squared. Let's see if we've got some of the similar stuff over here on our slides. As our analysis, we went through the similar steps. We distributed the outer sum along outside, giving us two terms. We factor our value a and b out. We simplify the first sum a, and we simplify the second sum, the inner sum there, giving us our n minus I. And then bringing our b all the way out. And on our notes, we brought the b out all the way out to start. That's the only difference here. Otherwise, we're at the same point here. Continuing, this is just copying from the other side. All right, so this is where we decide we need to simplify these sums. Again, we distributed the sum over the two terms. The first one was easier to simplify. The second one we left as it was there. So again, simplifying that to the bn squared, which we had. And again, this is where we looked at Gauss's sum, which has this closed form. Simplifying it. Let's see here. This concludes what we were looking at here. I had actually gathered these two terms together as well, but this is the same form. So our second method has to do with a simplification of this sum with a technique that I call reversing the sum. And the way to do this is to look a little bit closer at the actual terms in the sum. So one thing we'll notice is the first term we sum when I equals 0, when we plug in here, we'll get n. Then this sum, the next one we'll get is n minus 1, and so on, all the way down to, well, let's be careful here. When I plug in n minus 1, I'm going to get n minus n, those cancel out, and then minus a minus 1 is a plus 1. So we get all the way down to 1. So we'll notice here that this sum is asking us to add up all these numbers in this order. And of course, I hope we know that if we added up all the numbers in the opposite order, we would get the exact same thing. So this sum, we can rewrite it in the opposite order by starting at 1 and going up to n. Okay, and then just writing I as the index that we're summing over here. Okay, now this, we notice, is a little bit easier to solve than this. So this technique, which again I call reversing the sum, is useful, and it's particularly useful to get rid of these minus i's that show up, or in our work they'll more commonly show up as this n minus I term. So I want you, when you're doing your sums, think about this n minus I term. If you see this n minus I, sometimes there's n minus I plus 1, something like that showing up, then think, hey, I could use reversing the sum here and maybe get myself a simpler solution. And by simpler, I mean now if we go back to our work, we'll notice that we can replace this sum here with this one. That's what we did with reversing the sum, and we already know what a closed form expression of that sum is, which is again that Gauss's sum that we just looked at. Plugging that in here, we get the exact same solution as we had above. Okay, again, both of them are sufficient for us to conclude that our bubble sort algorithm that we were looking at is a big O of n squared algorithm. Okay, so in this video we reviewed the bubble sort algorithm as well as some simple summation techniques to simplify and solve our summation that expresses the runtime of our algorithm, and we concluded that our bubble sort algorithm was an n-squared sorting algorithm. In my next video I'm going to revisit these techniques by looking at the insertion sort algorithm. All right, thank you, and we'll see you in the next video.